There we go. Let's talk about Mario. So I've taken a whole load of work doing variably pretentious job titles like head of engineering and chief technical architect and principal engineer. All these, all those job titles that sound a lot fancier than they really are. Because what I really like doing is making things, and I love making things. I love spending time with the people that make things, and I love trying to make them do things a little bit better. I've written a couple of kids' books about programming websites and games, Get Coding 1 and 2 in all good bookstores, etc. But recently, more interestingly, I made a Game Boy emulator. So what is emulation? When I say the word emulation, we should probably talk about it a little bit. Emulation is the practice of writing software on one system so that it can simulate the runtime environment of another, normally with the goal of running software designed for a different piece of hardware or environment. Now, there's a couple of different approaches to emulation that you can take. You have low-level emulation, where you implement the behavior of the raw hardware, and then the software designed for it should just work. And then we also have high-level emulation, which is where you attempt to run the software natively on your target platform and intercept and re-implement certain system-level calls. So most game system emulators are a mix of these two things, often emulating low-level hardware architecture while re-implementing things like 3D drawing calls in higher-level modern APIs. There are plenty of famous emulators, from games console emulators to operating system emulators, even to hardware emulators. So, if you're running any kind of virtual machine or a VM, that is a kind of emulation. So, when I say I built a Game Boy emulator, what I'm really saying is that I built a program that can run Game Boy software while the Game Boy software itself believes it's running on Game Boy hardware, which is a little bit of a tongue twister. But the most important question kind of comes first. Why on earth would you build a Game Boy emulator? Why would you do that at all? I know it is really a bit pointless, but that's kind of the fun of experimentation. There's a lot of different answers to this question, but mostly I wanted to see if I could. It is so often that we're forced to live in a brutalistic corporate hellhole where only things that have to exist for money get rendered into reality. This is the total opposite of that. No one is ever going to get paid because of this. I don't want to get paid because of this. And Game Boy emulators already exist. Please, 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 please don't use my emulator. Aha, and we're back. Okay, sorry about that. Clearly technical difficulties. Can you give me a wave if you can see me and you can hear me? Perfect. Thank you very much. I'm going to start this slide again. So why would you build a Game Boy emulator? Like, it is a little bit pointless, but there's a lot of different answers to the question ultimately, but I wanted to do it because it wasn't for money. I wanted to do it because it's not corporate and because it's not boring software and because it's kind of a different thing you can do with your skills. So if you want to play Game Boy games, please, I'm going to start now with, like, don't use my emulator. It's incomplete, it's possibly buggy, and I'm not going to help you wake the Windfish in Link's Awakening, right? But this story is a little bit different than that, and it actually starts in the 1970s with a game called Pong and an interpreted programming language called Chip 8. And what we're going to do is we're going to use it to understand what emulation really is before we talk about Game Boys and before we talk about Mario. And another way to make sure you can see my slides. Perfect. Thank you very much, everybody. Okay, so Chip 8 sounds delicious, right? So I'd started toying around with emulators as part of what I suppose now is a decade-long experiment in running coding dojos. I do a lot of training for teams, and especially web dev teams, and they're looking to upskill or pick up TDD or learn how to write better tests. So while looking for different puzzles for dojos, I plundered the archives of this wonderful old website called RubyQuiz, which is still online. It's on rubyquiz.com. Like, check it out if you're interested in this kind of stuff as a tangent. And what they did is they used to run weekly programming puzzle contests where people would literally email in solutions in Ruby. Cool. And I ended up running their Chip 8 kata quite a few times. It's quiz 88 if you're looking for it. And the Chip 8 kata provides a binary program written in a language called Chip 8. It's a machine language, and it tasks you with writing an interpreter for it, along with outlining the hardware that the program should run on. So Chip 8 has 32 OPCODES in total. And don't worry if you don't know what that really means. We're going to break it down in painful detail. And the program supplied by the quiz actually only uses a subset of them to make the quiz a little bit more approachable. Because I remember thinking like it sounded absolutely terrifying the first time I read it. Like, oh, cool, you want me to write an interpreter for a machine language I've never heard. That sounds like something I could do. So opcodes, machine languages, what the hell? Let's look at a quick example of how computers, and specifically our computer processors and our CPUs, work before we go any further. So when processors are manufactured, they're built to implement a specific instruction set. So this instruction set is the list of things that the processor can do. Anybody old enough to remember might remember the 1990s competition between CISC and RISC architectures, which stands for Complex Instruction Set and Reduced Instruction Set Computing, respectively. Now, these instructions, these CPU instructions, are what they were referring to. The instructions are built into the physical hardware, and they can be programmed using machine code. Now, every processor or family of processors has its own instruction set, and as a result, it has its own machine code. Now, machine code is strictly numerical, and it's a strictly numerical representation of the operations that a processor can perform. So you've got a lot of numbers that can work with a processor. And an opcode, shortened from operation code, is the part of the machine code which specifies what operation the CPU should do. As a result of that, at one level up, the assembly language for a given processor can be assembled into this machine code, basically compiled, and is a low-level abstraction over the instruction set of your processor. So when we talk about assembly languages, and people often will mention assembly languages, what they really mean is the assembly language for a specific CPU's instruction set. Now, the CPU in hardware implements operations, so things like add two numbers together, or take a number from here and put it in this memory location. And the opcode, when a CPU is running a program, tells the CPU which instruction to execute when it encounters it. So I appreciate this all sounds really abstract, so let's look at the example above and see where all those moving parts really are. So in the example, on the left, you can see the raw machine code of a Chip 8 program, and we're going to revisit this a few times. And that same machine code decompiled into its corresponding instructions is on the right-hand side. Besides the opcode itself, most instructions also specify the data that they're going to process in the form of operands. Just kind of think of them as parameters that get passed to an opcode. And normally, those parameters are a memory address or a register address. And a register, if you don't know, is just some memory that lives on the processor itself. So a memory address is just a number. It's normally expressed in hexadecimal, but they're just numbers, really, and they start at 0 and they count up to however much memory you have. So it's interesting because I remember in the 90s there was always a big thing, especially in video games, about 16-bit and 32-bit, and this bitness got used as marketing terms. So when people talk about how many bits a CPU, I suppose, has, they're referring to the largest number a computer can hold in its memory when expressed in hexadecimal. The more bits, the larger the total amount of memory a CPU can address. So a CPU that only understands 8-bit numbers can only understand the numbers 0 to 255. Therefore, it can only address 256 memory locations. A CPU that understands 16-bit numbers can only understand the numbers from 0 to 65,535, which again means it can only address a total of 65,536 memory locations. So literally, it can just keep a bigger number in memory. And each memory location can store an amount of data. So in the case of chip 8, a memory address stores 8 bytes of data, and the chip 8 hardware has 4,096 memory locations. Cool. So we've got some numbers, and we've got CPUs that can refer to locations. This is like the foundation of all computing. I think you could probably go away and say you've done CS 101 now, probably. If you have or you haven't. So when you use a higher level programming language like C# or JavaScript, the runtimes that execute these specific programs have been compiled down for your specific CPU architecture. That means that ultimately, somewhere, something has been translated down to machine code and is running on your CPU. And whenever you create variables in your programs, somewhere, something is putting things in memory registers. It's all buried under epic amounts of abstraction. Most memory manipulation is done by interacting with an operating system. The operating system decides what lives where in memory. Often if you're running C#, you've got the CLR or the netcore runtime. You're running JavaScript, you've got Node that interacts with the operating system. But when you write code that puts something in a variable, all the way down the stack, this stuff happens for every single line of code you ever write. So, after our crash course on how processors work, let's look at a chip 8 program and some of the opcodes that it uses. So the program in the top left portion of the slide is just the original Ruby Quiz chip 8 test program. It's a raw binary file in the machine language of a chip 8 computer that, when opened in a hex editor, looks like that. To interpret this program, you would loop through each of the bytes. And if you look at the snippet of C# on the left, on the right even, we're just loading this file as a byte array and printing it to the screen. So in C#, the bytes are all represented in base 10 as integers, but notice how the first number that gets printed, 97, is the same as 61 in hexadecimal. And if you look at the first 2 digits of the original program at the top, this is that same 61 in the start of our test program, those first two numbers. So our documentation shows that our chip 8 interpreter operates on 2-byte opcodes. So to run this program, we need to loop through all of our pairs of bytes. In this case, we read 61 and 77 together. And then we process them according to whatever the hardware behavior is. And that's the very, very foundations, the fundamentals of emulating anything. So let's zoom in on those first 2 bytes from the file, those 2 hex numbers, 61 and 77. The 2 of them make up an opcode and its operand. So if you look in the manual, they call this 6xkk. And it's explained in the original Ruby quiz as setting the memory location x to the constant value kk. in this case 6177. KK is an 8-bit constant. It is literally the hexadecimal value 77, so it's the number 119. That's what it means. So our first opcode says 6, that's the opcode, 1, a constant, the memory address 1, and 77, the decimal number 119, which translated into English says, put the hexadecimal number 77 into memory location 1. So if you imagine memory locations as an array or like a big Excel spreadsheet for all I care, you can interpret this entire chip 8 program by implementing each one of those opcodes and writing a little bit of code to perform the logic with the different opcodes, in this case the number 6, doing different things. So this is a scary looking problem, but it's actually not so complicated under the hood, because when you do that first Ruby quiz, you realize the solution to it is a switch statement with like 8 cases, and that's it, right? That's the whole, the answer to the quiz. Sorry, spoilers. But the great thing about it as a challenge is because it's so far out from what people normally find themselves working on. People attending the dojos where I ran this quiz always found it exciting because like they felt they were making progress in something a world away from their normal work. And I ended up running this particular coding dojo a lot with plenty of different audiences because I think there's nothing more fun than taking people who think their only real skills are taking numbers from a database and putting them on web pages and showing them just how capable and awesome they can be with like a little bit of lateral thinking, and that really programming isn't just this horrible, blunt commercial thing. It can be fun and challenging and enjoyable. So like the end, right? Cool. Go do chip 8. I jest. You now know how to write an emulator. End of demo. No, let's talk about Game Boys. So chip 8 is a useful introduction to this kind of low-level programming because there are only 32 relatively simple opcodes to implement, and the Ruby quiz kata even more so because it only uses so few of them. The principles are exactly the same, but if I was to take you through every opcode in a Game Boy, it would hurt your brain. It's really important to remember that anyone can do things like this, right? So I'm not a particularly incredible programmer, but I can read and I can reason. And I really wanted to know that if given a background of building smaller machine code interpreters, I could do something bigger. And so Game Boys are bigger. So what's a Game Boy? More or less, literally nobody ever asked. I'll do the Wikipedia thing first. A Game Boy is an 8-bit handheld game console developed and manufactured by Nintendo. The first handheld in the Game Boy family, it was first released in Japan on April the 21st, 1989, then North America 3 months later, and lastly in Europe over a year later. It was designed by the same team that developed the Game & Watch and several Nintendo Entertainment System games. I don't know whoever writes those really, really dry things for Wikipedia, but it is a life skill. I mean, we all know what a Game Boy is, right? And they're absolutely iconic. You can set them on fire, apparently, and they still work. True story. They saw off about 50 billion competitor consoles by being simple, accessible, resilient, and fun. Like, this is my childhood, legitimately. This is my childhood in a little plastic mold. It's where my lifelong obsession with games probably came from. And I literally just typoed game from in my speaker notes. Like, Game Boys are freaking awesome. And personally, I remember growing up in Asia in the 80s, and I got my Game Boy. I don't know if you can see it here. This actual Game Boy, the screen covering just fell off. I got it in the Temple Street night market in Hong Kong, and I remember being a kid, like so excited and looking at the big walls of like colorful box art cartridges in the game stores. Like it's a proper emotional thing. So not only is the Game Boy awesome, but like it feels somehow deeply personal to me. But we don't care where you bought your Game Boy, I hear you all thinking. Programming. What is a Game Boy? Fine. So the Game Boy has an 8-bit 4.19 megahertz CPU. It's got 8 kilobytes of RAM, a 160 by 144 pixel display, and the Game Boy CPU is similar to an older Intel 8080. And most of the assemblers for it use Z80 style syntax. So it's a custom chip, but most of the instructions are similar to other well-known processors. Cool. So I read those technical specs, right? And I was like, yeah, I felt emboldened. It's just like the Z80. They're like really old. How hard can this possibly be? Well, I adore games, and I always have. And I love the 90s and 2000s emulation and porting scene, right? But a few things specifically ended up sending me down this path where I thought, oh, how hard could this possibly be? So I watched this really great YouTube video on a channel called Modern Vintage Gamer. I don't know if you've ever seen it. This guy's wonderful, and he did a time lapse video of him porting the game Another World to the original Xbox Live, and he did it like live on stream. And I'd spent some time in the past couple of years transliterating software for various clients. So when I say transliteration, I was porting Python and Java into .NET and .NET Core, and quite ironically porting a lot of .NET Core and C# stuff into TypeScript and JavaScript. So I felt kind of confident transliterating between these languages, and I've been working on some C and C++ hardware projects around building wearable LED displays. So I kind of thought, hey, like the Z80 processor, it's not too different from Chip 8 in complexity. Totally not true. I wonder if I can write a lo-fi Game Boy emulator and we could use it to capture frames and build some like mad wearable Game Boy. That sounds cool. To be confirmed. And so I fell into this black hole of 1990s era PDFs about reverse engineering the Game Boy. And you know, like when you fall into those Wikipedia black holes that you lose like 4 hours to, and you end up reading about the capital of a country that didn't exist after 1965? This was one of those holes, and it ran really, really deep. The 90s were wild, man. So I spent about a day reading this thing called Pan's Docs, a 25-year-long community effort to catalog all of the details of the Game Boy hardware. This is like some peak 1990s era deep technical reverse engineering. It's like totally a headful. They're wonderful docs, but I'd probably not recommend them as casual bedtime reading. You know, the no plot, the characters are boring. I skipped to what I felt was the most interesting place to start, which was loading some information from cartridges. And I opened Visual Studio and I started to code. And I wrote that. So, while from the frame of reference of writing an entire emulator, parsing a cartridge might not seem like much of a big deal, but I managed to get it done pretty quickly. I grabbed my copy of my totally legally backed up Nintendo, I promise, Super Mario Land ROM. Right here, it's fine, this is mine. In case I need an alibi. And I managed to parse the boot logo, right? And the cartridge information and the metadata within a few hours of hacking around. And I was like super excited because I could read the text Super Mario Land. It felt real. Like I had some virtual memory. I made myself a CPU class and some opcodes, and I was like, yes, I'm gonna do this thing. Then I got really catastrophically stuck. So I felt like I had a reasonable grasp of the Game Boy hardware, but I couldn't understand what some of my opcodes were meant to do. And my emulator kept crashing in its boot sequence. And to make matters more confusing, the documentation, now I do not have like an electronic engineering background or anything, it started using notation that I literally didn't understand. I couldn't even read the docs. And I'm sure it's some fairly like standard high school maths, but it was totally boiling my brain. So I was trying to implement the opcodes for the Game Boy CPU, just like in our earlier Chip 8 example, and I kept getting lost in the documentation, and I was stuck. So, not to be deterred, I went hunting for some other code bases that had been here before in an attempt to find something that could literally help me read the documentation I was looking at. And the Game Boy is quite a popular like first emulation target because it's relatively accessible. So I found a couple of emulators that worked in a couple of different languages. And I stumbled upon a project called CoffeeGB, like a working emulator in Java 1.8. And like this is wonderful. This is a revelation. Like I opened up the game and it worked. I could clone it, I could reason about it, and it was in a language I understood. So at this point, I figured I could try transliterate this MIT licensed open source code base and use some of the tests that were written for it and then kind of glue the things together at the end. And I started off by, I lost an entire day converting CoffeeGB from Java to Kotlin. Like it worked, but there wasn't really any point. Like I thought it would make it look closer to C#, so it'd be easier to port. And then I decided to just commit to doing a like-for-like full conversion, a full transliteration of the Java source into Netcore 3.1. In an attempt to hopefully understand where my opcode processing approach had differed and where my code was crashing on boot. So I keep on using this word like transliterate, so let's talk about that in deep detail. This is originally a language term that means to write or print a letter or word using the closest corresponding letters of a different alphabet or script. So for a little bit of clarification, a transliteration, as opposed to a full-blown software port, is a line-for-line cosmetic-only change. Like we're literally going to change the minimum amount required to get the software compiling in the target language. And then we will end up doing subsequent second and third passes to turn that transliteration into a real port for things that are missing or don't quite convert like for like. So porting and transliterating software is a very, very specific discipline, which is counter to how I'd normally build software. And ultimately, you have to think about it in three passes. So firstly, you have to transliterate until it compiles. So you work from an entry point down, normally involving starting at the main method and only migrating code that gets called file by file. You end up with lots and lots of stuff commented out. So secondly, you port over any test suite once the transliteration is done and ensure that the tests match the original. So you've converted form and function. And then thirdly, you convert the code to be idiomatic in its host language. So that's what I would normally regard as actually porting software at the end, like changing the way something worked. So in the examples above, you can see how the Java is subtly changed into C#, with package declarations swapped for namespaces, attributes being removed, and later much of the syntax being converted into C#8 using expression-bodied methods. So this is a fairly trite and succinct example just to fit on some slides. And some of the other conversions are far, far more dramatic. So it might seem like a set of obvious steps, but you have to do some really unnatural things sometimes that are going to totally go against your instincts. So during the first phase especially, you're going to often find yourself fighting your tools because you're at a disadvantage if you diverge the code in any way that prevents like-for-like comparisons. This means you're going to have to keep all the naming conventions. You're going to have to keep the casings and odd, non-idiomatic qualities of a foreign code base precisely as they are until you get to a point of safety. You're going to have to get very, very comfortable just throwing not implemented exceptions like everywhere, where a direct equivalent is not available until you've managed to get the code executing. And the sooner you can start transliterating any available tests, the better, because you're going to start to know early on if you're going off track. So ideally, to do this, you have to have a good enough reading grasp of the source language and a relatively advanced grasp of the target language to be able to convert some of the more subtle differences. In this particular code base, so something you may or may not know is that Java has quite rich enums, and you can put behavior load into enums in Java, and we totally lack that in C#. The construct just doesn't exist. So producing similar syntactic constructs that could be used in the same way is important. And I ended up like stitching extension methods onto enums and all sorts of crazy stuff. And what that does is it requires a reasonable mastery of the target language to pull off without getting yourself confused and stuck in a non-compiling code base. So once I found my groove with transliterating the CoffeeGB code base, a couple of things became apparent. Firstly, the UI would not port at all, just like not at all, not even remotely, because it was a bunch of JWT Java window toolkit code. And there was absolutely no point in trying to convert that like for like because I wasn't here to produce a weird C# port of JWT. So the JWT code was also responsible for drawing the game on the screen and handling controller inputs, So cool, fine, I've got my to-do list. There's two things that are going to have to be completely different. My first target quickly, as a result of that, became to get the headless mode in the original code base booting a Game Boy cartridge. So headless mode was designed to run the emulator without visual output or controls in a console window, and it was used in the test suite. I just figured if I could do enough to get that running, I could port the unit tests, and then I could exercise some of the community-authored homebrew ROMs that are designed to test various aspects of the Game Boy hardware. And I deleted all the JWT code, and I maintained all the code paths that called into it, replacing the method bodies with not implemented exceptions. I implemented a few interfaces with empty implementations, and I managed to basically cajole the headless mode into life. You can, if you look at the screenshot, you can see the code for headless mode as it still exists today in the source, passing in null displays and controllers and sound, along with amusingly the remnants of some JWT stuff commented out for reference. So I can't state enough how well compartmentalized the original code base was. And I was very, very lucky when it came to writing a new display that the original code kept an array of internal pixel colors packed into integers, right? And those integers combined with the various graphics opcodes produced a display image. And I knew that all I had to do at that point was convert an array of XY coordinates and find a way to just like get it on the screen, because I had pixel colors and locations. So I extracted the RGB values from this packed integer, and I raised a C# event in my new bitmap display class. So I did this to match the original implementation and made sure that the display is running on its own thread, which refreshes distinctly from the CPU emulation that's ticking at the same time. I just needed something to subscribe to my event with all my pixels and draw them on a screen somewhere. And yeah, legitimately WinForms to the rescue. Like, not even joking. You totally heard me right. WinForms. So let's just unpack this here. I ported a Game Boy emulator to .NET Core 3.1 just to run it in a WinForms UI, and I'm totally not sorry, and I would totally do it again. The number of questions I got, my sanity, why I wasn't using WPF, if anyone still used WinForms, if you could even run WinForms on .NET Core, were all totally excellent. People kind of forget that WinForms was designed to be so easy to use and really rapid application development friendly. And it lets you get stuff on the screen really quickly, right? So WinForms is secretly kind of awesome. And it also, I believe, last year was ported to run on .NET Core. So it totally just works. Obviously, .NET Core only on Windows. So in about 200 lines of code, I had a WinForms UI with a picture box on it that I could update with the current frame every time the emulator raised an event. If you're eagle-eyed and look closely through the background images here, the other thing that came free with WinForms was input handling. So I could hook an implementation of the controller up just like the JWT thing in the Java code base did. And I could hook them up to just WinForms key press events. So yeah, like WinForms is amazing. Don't quote me on that. And it kind of worked. Like totally kind of worked. So once I got to the point where I had the title screen of Mario booting in C# and side by side the original Java code base booting the same game, I realized that I'd made some kind of terrible error where my game would crash as soon as I started running it. So obviously enough of my port was working that there was stuff on the screen, right? And establishing where my code diverged, on the other hand, was very, very tricky. So luckily, I'm not the first person to ever try and write a Game Boy emulator. There's this like really great set of homebrew test ROMs that exercise different parts of the Game Boy hardware, which I could run in both emulators to see where they diverged. They're wonderfully named Blarg with 3 Gs and Mooneye, which are test ROMs. I think the Mooneye suite is actually from a work-in-progress Rust emulator. So I ported the test harness across from the original code base, and I got these test ROMs and I had them running. And as I suspected, the tests that were passing in the original Java code base were failing in my port. So I'd made a mistake. And this was a great first step because I had failing tests. I just needed to find out what and where I had broken something. So I mentioned earlier the idea of low-level emulation, where you're emulating the hardware. Well, both of these emulators are low-level emulators. And what that means is they literally implement the opcodes of the hardware as code, and they tick at the clock rate of the CPU. You can't meaningfully step through the code because the number of operations that you have to complete at the clock rate of the CPU to see any actual change in memory state is like, I don't know, it's a really big number. It's a lot. It's many, many, many operations, hundreds of thousands. So, but that's okay, right? We live in Visual Studio. And we have amazing things like conditional breakpoints that can help us see where values change, right? Well, ironically, the performance overhead of applying a conditional breakpoint to one of my virtual CPU registers was so severe that I couldn't even get Visual Studio to process the test cases as far as the first error in less than 10 minutes on like a top-end Ryzen. It just couldn't churn through the numbers fast enough because clearly VS was hooking in its debug process. So I knew that I'd get both code bases. If I could get both code bases to a breakpoint where their memory states diverged, I could totally solve the problems I was seeing. I just wasn't immediately sure how, because when your debugger doesn't work, what do you do? I was suffering from this pain of my integration tests being my main tests, right? Like a common pattern in all software. So I spent a morning building some tools. I started by building a debugger. I built a debugging tool with a client in both Java and C# that would keep the ticks of both emulators in sync. And it would break them both into the regular debugger when their memory state differed. So both emulators would call a HTTP server with the hash of their current memory state. And when it differed, I'd tell them to both pause. And it was really nice in theory, but in practice, it only helped me find one bug. Because obviously, if Visual Studio's built-in conditional debugger was slow, making network requests over the network as we step forward was definitely more slow. So it was a little bit too much overhead, and I thought, okay, cool, I can't do this. Let's go lo-fi. So I built a logging function into each emulator that I could wrap around the test cases that dumped the memory state to a massive log file on every single CPU tick. I knew that when the test passed in the first emulator, because they kind of ran at similar speeds, I could stop the failing test if it was still executing in another emulator. The number of lines in the file would tell me how far I'd ticked forwards. And what I ended up doing was doing lengthy diffs of these many gigabyte long log files. Like you run these tests for 30 seconds and you'll have 4 gig of text to find the tick number that the emulators diverged on. So I just did a diff tool and I found the tick number. Once I had the tick number, I added an if statement to my emulator with a debugger break when the tick number matched. To the world's most lo-fi debugging technique. It was important because I kept the transliterated code base very close to the original while I was doing this testing process. Actually, this debugging worked and wasn't a nightmare. So I could put the same shaped if statement on the same tick in both code bases and get both of my emulators frozen in a breakpoint. You know what? Like the sense of accomplishment you get from building your own debugging tools and it actually working is insane. Like it felt like magic when I actually managed to get these 2 damn emulators into a breakpoint that matched. It took about a day's work, but I had them both in parity with the original source and I could start refactoring. So what was the bug? What was the crashing bug? So I fell foul of converting one of the Java data structures to C#. So in Java, as I mentioned before, enums can have methods. And I'd hastily transliterated some of the code that categorized enums for the different memory banks in the GameBoy cartridges. So you'll notice if you glance to the top right here that enum names are used to categorize different parts of the same type of memory. For instance, ROM MBC3 and ROM MBC3 RAM are both identifying parts of memory that make up MBC3, which is a memory bank controller inside a Game Boy cartridge. Game Boy cartridges use this idea of memory banks to expand the amount of memory available to games. This is why the size of the cartridges were used in marketing material in the day. Games with more data, more switchable memory banks could get larger and you could store more graphics. So the bigger the size of the cartridge, generally, the better the game looked. So the code in the emulator that implemented the opcode to switch between memory banks needed to check if the current memory location was part of one of these memory banks. Now, the original Java implementation used a regular expression to check if the name of the enum member contained the name of the memory bank it was looking for. So it seems nice and simple. So I had hastily replaced that with a string contains call that presumed that the enum member would always have an underscore followed by the MBC value followed by an underscore. Cool. Which works totally perfectly well for the string rom underscore MBC3 underscore rem, but not so well for rom underscore MBC3 because it lacked that trailing underscore, right? So while trying to switch memory banks, my code was crashing, quickly replacing my string contains method back to the original regular expression, totally fixed the bug. It's likely that there are plenty more idiomatic C# ways to mark up enums. Normally, you would add attributes to provide this kind of categorization and do some kind of meta programming, but you know what? That's probably a little bit too slow. So one of the final entertaining surprises was the afternoon that I lost trying to work out why my emulator was slow. So on a related note, you'd be really surprised what a difference to performance release builds make. Like, those buttons do mean something. So I spent what felt like an eternity trying to profile the performance of the emulator because I couldn't work out why it was performing so badly. And the irony was it was because it was being observed. The program was ticking so fast that the overhead of collecting metrics and debugging in Visual Studio slowed the program down so that the two emulators side by side, mine was noticeably slower. Simply compiling and running in release mode and without a debugger attached showed that it was running totally fine, totally as benchmarked, and used minimal CPU. So I've kind of skirted around the audio in the emulator because, well, awkward, there isn't any. Yeah, I've not written it yet. I've never really done audio programming before, and I'm looking into various audio wrappers, probably starting with N-Audio to see if I can work out how to make the audio sing again. Because I don't know about you, but when I look at the Game Boy cartridges, like I can hear the theme song to Mario playing in my head when I see this picture. It's that like iconic. The original Java implementation used a very, very Java open source audio thing, which again, just like I didn't want to port JWT, I probably don't want to port an entire audio library to make this happen. So throughout the first couple of weeks of this project, and given that we're all in quarantine at the moment, well, the unlucky ones, I'd been teasing the internet with screenshots of Game Boy games relatively hard. So once I got to a point where the UI wasn't crashing and the code was suitably ported, I just kind of picked up the emulator and stuffed it on GitHub and shared it around, right? Mostly for the fun of it. And generally, people have enjoyed seeing this kind of project done in C# rather than like yet another business application, yet another boring like data access example. Oh, and I stuck like a ridiculous ASCII art renderer on the command line, so you can technically play Game Boy games in ASCII art if you want to, which was kind of fun. Because why would you not want to do that? It took like 20 minutes, and really that was the reason for doing it at all, right? Like that was the reason. So C# is a language I totally love, and a language I feel very comfortable with, and I love the direction that .NET Core, .NET 5, .NET, whatever the branding is this week, is taking at the moment. And I'm on a bit of a journey to prove that really any place that another language can do something, .NET Core is at least as good, at least as performant, and often plenty more beautiful at doing the same thing. And it's kind of wonderful to see people being really responsive and taking it in that spirit and feeling the same way. So, though obviously, when you put something online, it's let's say it's not without its detractors. Never read the comments. They say never read the comments, but I'm a glutton for punishment, and I like to engage. And there was one comment that really both stuck with me, and I think is important enough to highlight. Code quality is questionable. Here's how the author omits frames. They create a new image. They iterate over every pixel. They convert its value to a string. They pass it back as a source. They create a memory stream. They encode it as a bitmap. They call to array. This is some Electron level resource wasting. Reddit, as ever, is a mixed bag. So totally true. I had a bunch of really interesting conversations with people in the .NET and C# subreddits, and the general programming subreddit, on the other hand, absolutely not so much. It's really easy to forget how hostile people can be to absolutely nothing at all. But legitimately, this was one of the big takeaways of this process for me. Like, as programmers, we can be short and snipey and dig through code contextless, taking swipes at things, basically just bringing each other down. And like, that whole comment is totally true. Like, it could definitely be better. But like, you know what? The program consumes 30 to 50 megabytes of memory in total. I benchmarked it. And I would do this all again in exactly the same way, in a heartbeat, to put something cool and working out into the world that people enjoy. So let's hear this loud and clear. No gatekeepers, no perfection. Like, there is no such thing. Do the fun thing, enjoy yourselves, and share stuff, or we let tedious bores like whoever that guy was win. Luckily, the bores never win in the face of people doing cool stuff, right? So within a day or two of pushing some tweets out with links to the code, I already had 2 pull requests. One with a monogame UI that let the emulator run on various devices, the other with an Avalonia UI that let the emulator run on Linux and Mac, as well as the existing WinForms UI that I glued on the top of it, and the headless cross-platform ASCII art head CLI. Oh, and you can also reference this emulator as a library in your own .NET projects if you want to use it, which is amazing because literally in the last 2 weeks, there's a guy that's just done like a Twitter plays Pokemon thing, where you can tweet him Game Boy controls, and his user picture changes to control a game of Pokemon that uses this behind the scenes. And I got a message literally 2 days ago of someone who's doing a similar thing with like a Discord plays Pokemon, where he's averaging the chat inputs and streaming the image snapshot straight into his Discord channel, right? This is what happens when you do fun things. You let people build cooler stuff on top of it. So, you know, the takeaway for me is that I'm very happy I didn't give up when I got stuck. This isn't the journey that I thought I was going to go on when I started writing this, but that's fine. Like, I know it sounds trite, but everything we do in software is built on the shoulders of other talented people that built things before us. And it's so easy to get stuck and give up. And it's hard to go and decide to look around for inspiration. So I'm really, really thankful for the wonderfully high quality Coffee GB code base that I have the pleasure of adapting and merging with my own efforts. I'm really happy that I didn't succumb to my own hubris and decide that if I couldn't just work it out on my own, that it wasn't worth doing. And like, I'm absolutely thrilled that by sacrificing that little bit of ego, there's something cool and fun that people can play with and adapt and do their own thing with as well. So from my end, I really hope that you all have fun maybe pushing some of this code around or tearing it apart or seeing what you could do better, right? That's the point. And that's the talk about Game Boy. So I'm going to do a really, really quick demo, but you can obviously find me on the internet in all of those places, on the Twitters, on email, whatever. Please ask me questions. The code is on GitHub. Rip it off, steal all the stuff. And let's run it. Let's run it for a bit of fun. Here's the actual emulator, and it can load a ROM, and we can play Super Mario in C#. That's the real thing. And that's the end of the talk. Does anyone have any questions? I'm going to stop sharing my screen so I can see all your beautiful faces.
I don't think you need sound because the music was playing in my head when you were doing that anyway.
Right? Like exactly that. Like just everyone just hum along and you know exactly how it works. No, I love it. Like it was such a fun thing to do, honestly. And it's been so good to see people pushing the code around in ways that I didn't have the time or the inclination to get done. And the wild thing is, it was only like I think I spent 2 weeks on it, like 2 weeks as a day job. I was getting up in the morning and working on it and working on it. And it's kind of amazing what you can do if you just read the docs. Honestly, just read the docs and march forwards. Cool. Well, thank you so much for coming, everybody. Like, if you let me see if I can get a link in the chat as well of the GitHub if you want to have a play with it. GitHub. You'd think I would prepare all this in advance, but I don't. It is. Where is the chat? That's a more interesting question. Okay, cool. Everyone enter chat messages. Cool. Yeah, sorry about the technical error in the middle. My internet connection decided obviously this was the perfect time to disconnect for about 2 minutes. So I hope there's no glitches in the recording. Perfect. Thank you so much, everybody.